Hello, everybody. I'm going to go through the solution of question 40 in calculus section of the course Maths 1151 at University of New South Wales. Now, in this question, we define ln x as an integral from 1 to x dt over t, and x run through from the 0 to the infinity. Given this definition, we would like to prove these four cases. Ln xy is equal to ln x plus ln y. And if this condition happens, we would like to prove that ln x is always smaller than ln y. The range of ln is the real numbers, all real numbers. And there exists an inverse function for the ln function given this definition. So these are the parts that we would like to prove. Now, for this one, let's start. Ln xy, by the definition, you have x here and as comes out as an upper boundary. Always you have a lower boundary is 1. So when with respect to this definition, ln xy will be 1 up to xy. So only the upper bound will change. All the others will be the remaining same. So we would like to write this one as a sum of ln x plus ln y. So we need to play with this integral a bit. So one sensible thing to do is just to change a variable. Let's say u is equal to t over x. Right? This is just a change of variable. When you take the derivative in both sides, we will have dt. So x behave as a constant. We will have du dt. We need to look at what happens in the boundary. When t is equal to 1, u will be 1 over x. And when t is equal to y, c is equal to y times x, then we have u is equal to just y, right? xy, t is equal to xy. If you put xy here, x and x will cancel out. You will get only y. That's u is equal to y. So this can be written as 1 over x to y. X, which is dt. dt will be x du, which is this guy. And then the t will be u times x, which is this guy. So x and x will go. Only thing we have 1 over x to y du over y. Since xy is bigger than 1, 1 over x is smaller than y. And then, but we have other cases, right? 1 can appear before and after. So these cases will make the differences in the certain things. So we need to think about when 1 over x up to 1, maybe this is the case, or 1 over x will be bigger than 1, but it's always smaller than y. And maybe 1 over x and y, both of them will be below 1. So that's the case, right? I think you believe in me now. So this is the one case may happen. This is another case might happen. This is another case happen. Because one could be here, one could be here, one could be here. This is 3 cases, 3 possible cases. So this is what I'm saying here. Let's have a look at the first case. 1 over 1 appears between 1 over x and y. If this happens, y1 is the case. Well, important because it's the definition of the ln. Ln xy is defined as an integral from 1 to x dt over t. So 1 is the crucial number for us because we want to divide the integrals into the different pieces related to 1. So ln xy will be 1 over x1. We need to look at this guy. I'm not changing anything. I'm just changing t is equal to u. It doesn't matter because this is just variable. And then you have, since this happens, so I'm separating the integral from here to here plus here to here. This is what it is. And this guy here is actually, this is lny, no problem with that. This is just an lny. This one is negative, but this part is ln 1 over x. So we need to get this part as ln x. This is what we would like to prove. So this one is equal to ln x. If we do that for this case, we will be able to prove what we want to prove for this part. Okay, so we want to prove this, which means that we want to prove this is equal to that one. Again, we are taking the, this is a little claim. I'm just doing a little extra proof with respect to this equality. So the claim means we would like to prove this. So if we say in this case, u is equal to tx, then du is equal to xtu. For t is equal to 1 for the boundaries, u will be x. For t is equal to 1 over x, u will be 1. So this will be minus x is the boundary, and the 1 over x will be just 1. That's 1. And the changing the variable t will be just u over x, and the u dt will be du over x, which is this guy. X and x will cancel each other out. We will have du over u. So this is negative. I can change the order of the integration, and that will be another negative. So negative will be plus, but the order will be from 1 to x du over x. So this is exactly the ln x. This means is equal to ln x. So we prove this little claim here, and we put it back. We prove that ln xy is equal to ln x plus ln y for this case. Yep. Now, second case, if 1 over x is bigger than 1, what will happen? In this case, I can separate the integral, thinking about from 1 to y, which is this guy, minus negative the integral in this part, which is minus 1 over x. So I can separate this integral, calculate this integral as this minus this integral. Right. So this one is ln y already, and this one we just proved as above is ln x. So this is just ln x plus ln y. This happened as well. So case 2 has been proved. What will happen for the case 3 if 1 over x and smaller than y, smaller than 1, I can separate this integral as from 1 over x to the 1 minus from y to 1. So this is what I'm doing here. 1 over x to 1 minus y to 1. This is how I'm separating this, this integral. So here, this is a negative. So by just changing these boundaries from up and down, then will be another negative that will give us a positive. And here we have minus of, again, ordering, changing the ordering, we will have minus. We know that this integral is ln 1 over x, and we, by the definition, this is ln y. We prove above that this quantity is equal to ln x. So we prove that ln xy is equal to ln x plus ln y as we required. So this was the proof of the first section. What we need to understand for the second section is this. So we want to prove that under these circumstances, 0 is smaller than x, smaller than y, as a finite numbers. Then ln x is always smaller than ln y. In order to be able to do that, we need to observe something. I think. I just would like to show it in one line. Okay, if x, well, I said I want to just make a color consistency in order to be able to explain what I am saying. So more visual rather than to explain what I am trying to say. I use different colors, and different variables as well, in order to be able to understand it. But x here, x0 here is just really the x is the variable. I just used another name for it in order to be able to explain what I'm trying to say here. This is a different cases. If x variable is between 0 and 1, then the ln x0 from 1 to x0 dt over t will be, by just changing this order, will be x0 because x0 is smaller than 1. If you think about this is a function, and we know that from lower boundary to the upper boundary, this function, there's a function here. If there's a function here, then this integral calculates for us is the area. So this knowledge we know that from previously. That's what I'm going to use. So ft is equal to 1 over t. Fx is equal to 1 over x, whatever you want. So this is the function that we are thinking under this function, under this curve. We have some intervals, and the area under these intervals give us the ln. So if x0 between 0 and 1, if 1 is here, then this point will be 1, 1 point. And any number between 0 and 1, the integral underneath here will be this area. But there's a negative here, like x0 is smaller number, 1 is bigger number. And there's a negative sign here, as we realized. Then the area here gives the negative of the area underneath here. This is what I showed as a smaller than 1. Right? I hope this is clear, right? For any variable between 0 and 1, ln x0 represents the negative of the area of this area. If x is bigger than 1, then the area under this curve will appear like in green area. For any x1 bigger than 1, it will be like here, or here, or here, or here. Because x1 is bigger than 1, and this integral will represent, sorry, there's no dt here, just a t here, gives area a bigger than 1. So that's the green area. Okay, this is a very important observation for this part and for the next part. And by thinking of this observation, now we would like to prove that ln x is smaller than ln y, given that x is smaller than y. Okay, we still need to think about the cases because the cases are different for x is equal like a x is equal to 1 case is different from the others, right? Smaller than x is equal to 1, bigger than x is equal to 1 are different. So we need to separately look at those cases. So what is the first case that we need to think about is when x and y appears between 0 and 1. Then ln x will be the negative of the area under this curve ft is equal to 1 over t from x to 1. So if x is here, then 1 is here. Then x is smaller than y. So x is here, y is here, and ax is here, ay is the green area here. But ax is positive because area is a positive measurement. Ax is a positive number, ay is a positive number. But since these are negative, and as we see in this, just visual, we know that ax, the area of ax is bigger than the area of ay as a positive entities. But since we multiply with the negative, then minus ax is smaller than minus ay. That means that ln x is smaller than ln y. This is what we wanted anyway. So in this case, we prove what we wanted to prove. Now, consider x is between 0 and 1, this is another possibility. I have three possibilities, right? So if x between 0 and 1 and y is bigger than 1, what will happen? So ln x will represent this area, ax under 1. So ax is positive, but the ln x will be the negative of this positive value. Right? Ax is positive, but ln x is the negative of the ax. And then whatever the ay is, it could be very, very small. The green area could be very, very small. It doesn't matter, or very, very large. It doesn't matter. You will always obtain a negative number on the other side. So ln x will be always a negative number and will be always smaller than positive number. So this is what we are saying here. So ln x is always negative and ln y will be always positive under this circumstances, under this condition. Then it means ln x is smaller than ln y. So under this condition, we found that ln x is smaller than ln y. So the last case, either x and y bigger than 1. So what we had, either x and y between 0 and 1, either x is between 0 and 1 and y is bigger than 1. And then the last case is maybe x and y are bigger than 1. What will happen? In this case, both area, ax and ny, both of them will be positive. But x area will be always smaller than y because y is a positive number bigger than x. Then ln x smaller than ln y all the time because ax is a positive, ay is positive. As an area, it can be seen by looking at the graph. Under these areas will be always ax smaller than ay. So this is proven. So this proves that for the section B. For the section C, we would like to show that the range of ln is the real numbers. From this above faction, from the section B, what we realize that if x between 0 and 1, if in this section, we can obtain every real number. If you come to think about it here could be very small or very, very large because this area, it goes to the infinity. So the area underneath of this one will get all real numbers, right? From minus infinity to the plus infinity. In fact, it really corresponds this curve over here for y is equal to ln x curve. That the area here will be the infinitely many from 0 to there. 0, we haven't talked about it yet. So 0 is not included here. What we realized in the B section, we have ln x. For every x between 0 and 1, we will obtain a number between minus infinity to 0 by just looking at the graphs and thinking about the area of it. And if x between 1 and infinity, then we will obtain all real numbers as area underneath this curve. So this is obvious too. The trick is that to understand what will happen when x is equal to 1, we didn't say anything about it. When x is equal to 1, by the definition, we will have the integral from 1 to 1 dt over t, sorry. And this function, it doesn't matter. If you're taking an integral at the point, we assume that the area of a point is always 0. So this is 0. So this includes to 0 when x is equal to 1. Then for each x's from 0 to infinity, ln x will be minus infinite to the plus infinite, which is the all real numbers. That means the range of a ln is the all real numbers. Now section D. This is about a little bit about functions and definitions. So the green areas, yellow areas are the informations extra for this section. It's not included as a solution of this, but I would like to explain what is an inverse function, what is the conditions of having an inverse function. So this is the first task that I would like to do for this question. So what does it mean a function is one-to-one on its domain? So a function is one-to-one if it satisfies this condition, which means fx1 is equal to fx2 implies that x1 is equal to x2. This condition implies that such things will not happen. Why I am saying it, if x1 and x2 is at one point in the range, then where they are coming from, it should be exactly the one. Right? So x1 has to be x2. So if a function is one-to-one, you cannot have this situation. You cannot have this situation, x1 cannot be different from x2. It has to be the same number such that it goes to the one number, one target in the range area. This is for the concepts of one-to-one functions. An important example to keep in your mind is if x is equal to x squared, because fx is equal to x squared is not a one-to-one map. If you think about the whole x's, because you have minus 2 squared plus 2 squared gives you the 4. Minus 2 squared is 4, 2 squared is 4. So real numbers here goes to the one. Two different numbers goes to the one number. So this is not a one-to-one case. Another way to understand one-to-one functions is a horizontal line test. This is the thinking about the graph into two-dimensional space. And this is also a quick way to understand it. But this is not a general definition. What I am saying here is much more general, and you can generalize it. It is true for every function, right? And the points could be any domain. So it is not one-dimensional, two-dimensional issues that I'm talking about here. This is true in general. It's a concept of the one-to-one map is this. And this is the just interpretations of the one-to-one map into two-dimensional space, since there are two, looking at the horizontal line test, which means the graph intersects each horizontal line at most once. So if you have a graph like that, so each horizontal line passes through the graph at one point only. But if you have this x is equal to y, if x is equal to x squared function, then any line of this kind, if you think about the horizontal line passing through this line, it's one intersection. But another line here at most once, right? And by many, many times actually passing through the 2 points. So this is not one-to-one. It's exactly what I said here. If x is equal to x squared is not one-to-one. So this is the general knowledge. An invertible map means, in general, is a map. There's an inverse of a map, if and only if that map is one-to-one and onto. Now, onto concept means that you have a function from the domain to the range, and range could be in another big set, for example, R prime. The function f itself is always onto on its own range. If you're taking whole range of the function, then f is already onto by the definitions of the function range, because the range means that you're taking any element in the domain, applying the function, whatever you get there on the other side is your element of the range. If this happens, if you have a one-to-one and onto map, then you have an invertible map. It's general knowledge. Again, still I'm doing an introduction. What does an inverse function means? A function has an inverse if f is one-to-one and on its own domain with range R. So with range here is very important because range corresponds to onto concept, right? This range is an important word here, which corresponds onto. Okay. So a one-to-one, and it's if you think about the range, and if you think about if you prove that the function is one-to-one, then it has an inverse. The last part of the question, we wanted to find out the inverse function of the ln function. This is why we are introducing these concepts again and trying to make it clear. So what this means, what does this inverse function means as a definition? If you have a function from the domain to the range, the inverse function is defined by taking any element f inverse b is equal to a if fa is equal to b, right? A is the domain, b is in the range. So if if it is not one-to-one, you will not be able to find out a function when you're going back. So f inverse needs to be a function, can be a function if and only if f is one-to-one. Otherwise, it will not be well defined. So this is why it is important f is one-to-one when you're going back. Otherwise, as you see from this picture, this may happen. You will have two different definitions for one element. This is an inverse function. It cannot happen. If this happens, you cannot define inverses because the inverse doesn't make sense. Inverse will not be a function. In order to be able to make a function is a sensible thing, is as well defined if it's only you define in one way. If you're defining a function in two ways, like 4 goes to -2 and sometimes goes to the 2, impossible. You cannot define a function like that. You cannot, this is not a well-defined map. A well-defined map cannot go forward to -2 sometimes, 2 sometimes, impossible, right? So this is what I'm trying to say. F inverse, you must have F one-to-one, such that F inverse will be a function. And if you take the range as a domain, then you can do this trick. If it is not one-to-one, you cannot do it. If this happens, this means that F inverse F D is the identity map in the domain. And if you take F inverse F, then that will be the identity map in the range. So if there exists an inverse. So what we need to do, I think it is clear now what we need to prove for this function. We want to prove that ln function is one-to-one. If we want to prove that ln has an inverse function, we need to prove that ln function is one-to-one on its own range. Okay, proof of this claim is that horizontal line test gives the ln function is one-to-one. This is pretty easy in the sense that when you think about the ln function, but we don't want to this way for this because we assume that we don't know this curve yet, right? This is the exercise that we are doing. We assume that we don't know this curve yet. So we want to prove this much more general way. We want to prove in a more general way, more theoretical way. Okay, so the property is that fx, ln x is equal to ly, and if this happens, we assume this, and we want to prove that x is equal to y. So if ln x is equal to ln y, and x and y is in the domain, then by the definition, this integral is equal to this integral. The area exactly the same if and only if x is equal to y. So for all Lx is equal to Ly, we have x is equal to y. So ln function is a one-to-one function. We know that this is the range because we've just proved in the previous section. ln function domain is 0 to infinity, and the range is minus infinity to plus infinity. Since it is one-to-one, there exists an inverse function when we define the ln function from domain to the range. And we say this inverse function of the ln, we give a name, we call it exponential function in general. In this case, the inverse function is the from range to domain. This is what I'm doing here. This is exactly what I'm doing here. I'm using a definition. The function, ln function from domain to the range, inverse function should be range to the domain, such that f inverse b is equal to a, if fa is equal to b. So this is what I'm doing here. So ln x to the exponential function should be the identity map in domain, which is there. And if I take inverse function, then the ln function, it should be the identity map in the range. Then this is what is here. This is the identity maps in the domain. This is the identity map in the range. This is just a shortcut in terms of the functions. This is identity map in the domain, identity map in the range. So this is what it is. I hope this is useful, and I try to explain it in a large way, but you need to only prove this for this section. This is the answer for the last bit, but I wanted to explain more in order to be able to make clear why it is. Thank you very much for listening. I hope it is useful for all of you. Thank you. Cheers.